So,
then put me co-host to be able to.
We say, okay, now my side's okay.
it's working?
Yes.
Oh my goodness. Oh,
It works.
oh my gosh. You know, I'm gonna stop my PhD and I'm gonna study the Zoom application.
Yeah, and
It's more hard.
To be able.
I will show you when we finish, Mesa. I will show you another way to do it more professional than this one.
Yeah. Okay, so should we start?
Okay, just 1 second. Okay, now we have to be okay because we are starting live.
Okay.
Okay, you can start, Mesa, now.
Okay. Hi, everyone. I'm so glad to welcome you today with us in another new session of Astro Talk. Today, our guest is Dr. Cyrine Abdo Nehmé, which she is astronomer at the Observatory of Lebanon. Cyrine, she had a PhD in astrophysics astronomy from the University Denis Diderot Paris 7 and Observatory de Maris Mouden. And also, she is member of the Scientific European Consortium for GWST, which is the space mission for the Jovian system for Jupiter and its satellites. And then her actual scientific field, which she work about supernova remnant and mass dust budget relation, and also about exoplanet-like detection, statistic, and characterization. So today, Cyrine, she wanna give us talk about supernova explosions. So let's get dusty with Cyrine. You can start.
Thank you so much, and welcome everybody. Thank you to invite me. I feel so honored, and I'm always here for the Arab region and the MENA region for astrophysics. Mesa, I just want to say something, that the James Webb Space Telescope is not just for the Jovian exoplanet. It is also for the infrared. It's also to discover and to study the beginning of the universe. You know, it's for for the people who are listening to us. It is the biggest monster who will fly with the biggest mirror at 6.5 meters. So, you know, not just the Jovian. So today we're not going to talk about Jovian, neither exoplanets, even if everybody is interested about the subject and searching for extraterrestrial life. I know why, maybe because we are fed up with this on Earth, but let's get dusty. What I speak with dots, I will present the work that we did with Jean Tedros, Marc Sauvage, and Sarkis Kassounian, and another work that we are writing, another paper that it is undergoing with Tedros and Marc Sauvage. So I will not talk about that dust. It shows that the last 2-3 weeks, we have more than 2 papers in Italy, one, and in USA, that are relating the pollution to the COVID-19, the amount of people infected. So I know that you are now confined. This is why we're not talking about that, but those are dust also. I know that you are confined, and dust can be everywhere at home, and you need to get them out, and you need to really get rid of that. And every time when your car is not very clean, someone will write, I don't know if in your countries also someone will write, please wash me, or in Arabic, arjuk ighsilni. So those are also dust. And in 2015, in the Arabian Peninsula, we had a big, really thick cloak of dust. And by the last study done by Dr. Diana Francis in New York University in Abu Dhabi, she said that those intense dust storms may become more common in the Gulf because of the Arctic worms. So you see that, and you are seeing that they are wearing masks because of those small dust. And then to get out from our houses, to go out from the city, to get out bigger and bigger, I'm gonna try to convince you that the space is really dusty. If we look at this image, on the left up, we have the dark dust of the giant elliptical galaxy toward the Centaurus A. So when we see the dust in the visible, we are seeing it as dark, absorbing light. On the right images, upper right, we are seeing in the spiral galaxy, we're seeing it in the arms, it is an infrared. And we see that dust particles, we see that dust particle in the galaxies plays a big role. Down, I will show you here, you're seeing in this image, the Lord of the Rings, my favorite planet, this is Saturn. And why we are seeing it like that, because the sun is just behind it. And it is, sorry, but I'm having people entering and I'm a host, so the sun is behind Saturn and we see the dusty ice in the ring of Saturn. And I'm just going to finish with this. You know, every one of you knows that the comets are made of dust. And I don't know if Joe Khoury is here. He is a fan of meteorites. Joe Khoury is my youngest fan. I think he has like 10 years or 9. And he wanted to attend this session. It's 10 p.m. in Beirut, well, 10:24 now. And the comets are made of dust. So you see that space is really a dusty place. One of my favorite images, and those are those huge field of view. One of the biggest one, if you see here, it is the Cyrine Abdo from left to right. This image, full of dust, full of
Cyrine, don't worry. I'm gonna to accept the participant. Okay, I can accept.
Please,
Don't worry. Go ahead.
Yes. So those dust, when you are seeing dark, there's a thick clouds, cirrus clouds. You're seeing a lot of stars that they are dying, and also on the upper right, you're seeing places of birth of stars because of the density of the dust. So we're seeing here in this big field of view, we are seeing a cycle of stars and dust. This is life and death of stars. And I really love really this image, and you see it is here on the wall. So it's inverted. Anyway, so in this picture, in this image, we have the life of the universe. So you can ask, but what are those dusts? Where do they come from? How we form them? But before this, you may tell me, yeah, maybe we heard about a star, we form a star, and the star will finish its stage, we will see it later, it will explode, and then to do more helium, and then carbon and oxygen. But, okay, so there was a place where we don't have any star. And, you know, like the question, the equation, who was before, the chicken or the egg? So, just, we didn't, I personally, I don't know the answer. I don't know if someone's here know the answer, but just for a very beautiful observation, we have cosmic primordial dust. ALMA and Hubble Space Telescope, as you are seeing here in the image, observed a very distant explosion of star and distribution of dust. So it is the MAC S041, forget about the name, but what is important, it was published in 2019. It is 13.2 billion light years. And I think that most of you knows the age of the universe. So you see that the distribution here, we have dust and oxygen gas traces by ALMA, and we have red and green respectively also. So you see that here, I will explain to you later on why we have discrepancy in color and information. So we have here gas and dust from 13.2 billion years. So you may think that I will not enter into the paper, into the details, but if you want me the details of the paper, I will explain it to you. I will give it to you. But you may think that at that time, 13.2 billion years, a star got the time to live, to explode, and to form dust. Well, maybe. And so this is a movie. It is a 3D dust map for thousands of light years in the Milky Way. It is not all the, it's just a cut. I'll try to share because it's nice to see it. It's I will stop this one and I will share the movie. I hope that I will succeed in it. This is why I didn't want to do it this way. If we don't have a choice, we do it this way. So what I will show you is a small movie about the distribution of the, okay. And to share it, I will go back here. Sorry for that, but it's really interesting to see it 3D. Is it orbiting sun? Okay, so this is a 3D simulation for a real position of the star distribution with the Taurus, Perseus, and you see that there are places. Yes? Yes?
No, it's okay. Let's go.
Okay, thank you. So I repeated it. So here we have this cut in the galaxy, and you're seeing the distribution. Those white are the distribution of this. So it is really, they are here. Our dots are here, and they are kind of everywhere. Let me go back to my slide. And to continue, why we study dust? Why this is that important to study the dust? You know that, maybe you don't know, but the stars are main players in the universe for the formation of star dust, the grains, and the gas. And when we have the amount of dust and gas, we will increase or decrease the rate of formation of stars. So the cosmic cloud in the dust and the gas, in the star formation, like we saw it in the Carina, for example, can tell us a cosmic history, can tell us how many explosions of supernovae, can tell us what the initial mass of a star exploded. So we have a lot of elements disseminated into the dust. And sometimes when we detect that kind of dust, we can know the kind of dust, we can know the processes that they are going into that place. Because dust by themselves are very sensitive to every radiation. So, and they are very sensitive to the components that they are present in the medium. We have several types of dust, and every type of dust will emit and absorb at specific color, specific wavelength. So the dust are not just those dust annoying. Our interstellar dust and cosmic dust are just a blessing. And I know for the stellar guys, we are just parasites. They don't love us, the guys who study the stars. And the important points also to study the dust is that one of my research were the formation of the molecular of hydrogen, and they cannot form those H2, those new molecule of hydrogen, they cannot form without dust. They cannot just take hand by hand, just two atoms of hydrogen. Yeah, let us just join together. No, they need a third part to do absorption, to see if they have energy. And then when they are formed, they kick the dust, they heat the dust, and they leave with a speed and the kinetic energy. So, and if we can calculate the mass budget of the dust it's emitted, I'm going to extrapolate a little bit. We can also, in this universe, we just see just 4% of our universe, the visible universe. So dust can absorb, dust can emit, dust can do excitation, so heating or cooling. So if we can calculate the mass budget of the visible matter, it is for me a nice idea to calculate the mass if we do the subtraction of the dark matter also. So you see that if dark matter exists, but it's another discussion, you see that there is a lot of points that they are important in the dust. But we have always a budget crisis, or to abandon not. Because when you form the dust, there are processes to destroy the dust also. Are the processes not efficient? Are the process of formation are not very well simulated? So I never repeat it enough, but those dust and grains can go from nano to micrometrical solid particle made of carbon and silicon. Okay, and they are formed by explosion of when the stars are dead for my supernova. So let us blow a star now, and then I will tell you about my favorite explosion of supernova. I will show you a small simulation. So I will stop this one, and I will share with you this one. Okay. I think that you're hearing, but you're not seeing. Okay. Ta-da! So, it's about time to talk about the crab. We are, and we have, let me just, so those are, I promise you, I think that those are the only movies I have. Okay, all right. So are you seeing it very well, or should I put it like this? It's better, I think. Okay, so it's a simulation from ESA and Hubble Space Telescope. What we saw here is a star at the age, very developed age, very old age, will explode and then will form the very specific and special one we'll talk about. But we observed decades the dust, and the wavelength, the domain of dust emission, we observe it in absorption. But you can tell me, yeah, what is the importance to observe darkness? Because when dust absorbed, we will see nothing. It's dark. So the wavelength chosen by dust is the infrared, far infrared, mid infrared. Even if we observed for decades, we are still struggling to explain the amount of dust present in every interstellar medium and in our interstellar medium, our galaxy, for example. And here there is a Gaia map. I forgot the year. I think it's 3 years ago or 2 years ago. I don't know. So it's the distribution of the mass between galaxies. These are the blue open cluster of the dust, the mass of the dust, and the globular cluster. So it is for the whole galaxy. And we need to be able to calculate that budget, to be able to understand the formation of the dust, to be able to understand the composition of the dust, and all of that, the interaction with the dust, with its medium. We need to revisit one of our beloved, and to use a specific one, which is the Crab Nebula. So what are you seeing here in this image are 6 images with different wavelengths. We start by the radio wave, the infrared radiation, the visible light, the ultraviolet, the low energy X-ray inside, which will rotate. We will have a pulsar that will take the material with the rotation and will do those filaments that we see in the visible, and the high X-ray, we see that it's kind of some pixels. So why I'm showing you those images, to tell you that each wavelength is very important for the explanation of the astrophysics. For me, any wavelength, always we study multi-wavelength observation, because each wavelength is a window to another view, to another look, to another angle. So we take this nebula And if you look in the image up, you see that this Crab Nebula, the remnant, it is, I put it here on the position of this crab, the upper one in the galaxy. You see that where's the cross? Where the cross is, you see this is the position of the crab. And in the, if we can get out from our galaxy and to look our galaxy from up, we can see that we are like here, and the Crab Nebula is a little bit distance, like this, like two half arms, you know, in between the arms. But the position in the upper image, the position of the Crab Nebula is very critical. Look at that emission. I think it's Fermi-like emission. And you see that the point Crab Nebula is not an explosion of a supernovae in a very kind of smooth medium. There are things around it. There are red things around it. The red is emission happening, things happening. And we wanted to also to revisit it, not just because it's a very complex, because the Crab Nebula, I think, if I'm not wrong, it is one of the commonly observed celestial objects in the galaxy. They observe it with all the wavelengths. It emits all over. And to calibrate, you know, and it was really kind of young, you know, if you can say that it was observed by a Chinese astronomer, I forgot the name, in 10,054. And at the beginning, when he saw it, you can tell me why it's called the Crab Nebula. It's not crab now, but when he found it was like some bulk with food and steps. This is why we observe it. It was very well observed, and we have some kind of clean view to it. Is complex, but not that complex, you know. And there is no dusty galactic material in front of it or kind of behind of it. You will see that this is not true, what I'm telling you here. Okay, so if we want to calculate exactly the amount of dust present in the Crab Nebula, we need to be sure that it is very well isolated. So those are several advantages, and we have a lot of advantages, and because I love a personal relationship to this nebula. And when we started to study the observation, with the new observation with Herschel, we looked at the other studies done, for example, by Gomez et al. 2013, by Tamim and Drake 2013. And Tamim, I just say hi to Tamim, she is really a fantastic woman, and Owen and Barrow 2015. And we saw that in Gomez et al., for example, they have calculated the mass dust by choosing a component of dust. I explained to you that the dust can be like carbon or silicate, small or big, and they did found a mass between 0.08 solar mass times the mass of the sun and 0.14 solar mass. So, and they divided it into two temperature components for two dust and warm. In Tamim and Dweck 2013, they did a total mass derivation with three dust composition, silicate and carbon mixed, and they found that it's 0.019 solar mass and 0.13. With Owen and Barlow, so we are calculating the mass with the mole methods. With Owen and Barlow, they found that it's 0.1 solar mass and 1 solar mass. So why I'm showing you those, it's not to pointing that it is wrong or right. It's just to tell you that we don't know really the value of dust in that Crab Nebula. I'm not talking about any nebula. So that remnant that is very well observed, that it has a lot of positive points, we are not sure about the mass. And here, because we have a lot of parameters, we have a lot of things to do. Why? This degree, this frequency. We have uncertainties when we calculate, when we do those calculations. Many uncertainties come from the sources of supernova remnants. If we have some parts that they are in front, background, and other stuff. The second reasons is that, do we really understand the properties of the dust? Are they really separated into small and big grains? Are they really composed? The composition is this carbon silica mixture? Our models, are they really okay? And also, one of the important things that I worked on with the guys on the paper is to measure really the pure emission of the nebula. And that is the question. Because there's a relation between the color emitted by the dust, which is the whole colors of the infrared, okay, far infrared, mid-infrared, and the infrared, and a relation to the mass, of course, with a lot of assumption. But even this, if you don't calculate the light, pure light, coming from the dust themselves, then you're doomed. You can have a lot of mass. Oh, okay. So this is, all right. So what are we talking about? Okay. So I just need to change this slide because it's the PDF. I think that we lost it with the PDF. And I lost it here also. Okay. Right. Just 1 second. I will flip it and you will see. So what I will show you here is that what we are doing when we, I just need to rotate this. Yes. Well, what we do when we calculate the mass. And I will share this one. Go back to Zoom. Share this. I hope that you are seeing better than this. Okay, I cannot show you better than that because the PDF, I think that the size is fine enough. So what are we talking about when I tell you that we need to calculate the, what happened? Am I still on or we cut? No?
Yeah, you are on, you are here.
Okay, and are you seeing what I'm sharing or not?
No, not as a state of now. No, not as a state of now, just see you.
Now.
Okay, yeah. It's working.
Okay, because I saw black thing. Okay, so what I was talking about is what we used to do is imagine that this is okay, it's not the shape of the nebula, but imagine that this is the shape of the nebula, and then we need to calculate the total flux as the light coming from the nebula itself. So the flux, it is the S, I'm going to certain wavelength, infrared, will be the total that I see subtracted by the background, subtracted by the synchrotron. And what is the synchrotron? When I showed you this thing, that's pulsar that is rotating, pulsating inside the remnant, it is pulsating on a very specific wavelength synchrotron. This synchrotron emission will not influence. So this is why on the right, we will do a model after the calculation of the pure light of the nebula, and then we related it to the mass of the dust divided by the black body emission. This is what you see, and the distance square. And this is how we calculate the mass budget from the emission, SIR. So imagine that in my equation on the right bottom, I have a problem, a huge problem to calculate the pure emission of the flux. So my mass would be really, one of the parameters, my mass would be really very, very well influenced. And it is. And it is. So I go back to the presentation. I will share with you the PDF file. I'm sorry for this again, but it's the best way for us to see it. Okay. So what we did is we took our the Herschel data. We worked on new data, and we have several observations, several wavelengths from Max Spire, and we did the photometric region observations. So it is on 70 micron, 160 micron, 250, 350, and 500. Those are the emission of the infrared. And we did what everyone used to do and doing the photometry. What is a photometry? So we are going to calculate, to put up. I hope that it's working. Okay, it's not working. Okay, so it's fine. You're going to see just that. So this is one of the images that we have. It's the full Crab Nebula field of view in 160 micron. You see that we have a complex background. You see that we have the crab in itself inside, but we have some bright things back. So how they used to do, I'm sorry because PDF did this, they used to proceed by photometry, means that, or take an aperture, a circular, or an elliptical. The ellipse here was just parallel to the target. But anyway, and then they took it off, they extract the background, and then they calculate the right emission of the, what's supposed to be right emission of the crab. What I'm trying to explain to you here is that if you have clouds in the mountains and you have someone is walking, what you would like to see is to get rid of the clouds to see him or her very clearly. And this is what I try to do here. You see that when we have the full flux, we're not able to be sure that. So what happened here, we calculate this, we just wanted to compare it. We have some similarity, but this is a problem. Why? Because if you look at the circle, you cannot, with the circle aperture, you cannot pretend, scientifically pretend that you are just targeting the remnant. Because you're taking a flux from the background also. And if you take also the ellipse is not good. So astrophysically and morphologically, the nebula, and especially the Crab Nebula, is really very complex and very not defined and stuff. So we cannot take ellipse, these are circle. And I did an example of octagon also. So no problemo. So we have a problem, but Omar Simpson always says no problemo. We have a solution. So to face this, we have developed in the paper that we published in 2019 a photometric method that they are much data-driven as much as possible. They will just calculate the contours, if you want, of the emission of the data. So it is called a kind of Otsu method. So it is an algorithm that tries to find with a separation criteria, a threshold, when the region of interest will stop. Means that we just try to calculate, to take rid really, to take just the crab and to take it out, to just try to estimate the background, okay? And as much as data driven without any eye choosing. So we did it with the object of region of interest, ROI. We define the first step, we take it off, and then we remove the background contribution. So I'll go into the details of the values, but what we found is also different. So we didn't different of anything that is what I stated before for the mass dust, for the 3, 4, 5 papers before, for the guys and the teams. So we found that, so this is the dust model that we use, everyone will use it, okay? We didn't play with the distribution of the grain, if they are carbon, or we just wanted to calculate the efficiency of the parameters. So we obtained that with one component, we can describe the temperature of the clouds, and we calculated kind of mass that is really different than the others. So the mass, total mass, it is 0.05 plus or minus 0.03 solar mass. So there we have 0.01, 0.01, not 0.01, okay? So we cannot say that we're right, we cannot say that they are wrong, I cannot say that we have the exact, truth. So what you have to keep in mind and to take home with you is that even by improving, and we tried to play and to do testing with the background, when we improve the method, the density, the flux density and the emission will change. The processing techniques that we developed are really important. So to produce the SED is the spectral energy distribution of the dust, of the emission. It's not just, the problem is not just for the dust to know the composition, is also to know what is emitting where and how. And this is the challenge, if you want, to really clean the background. So we did try to clean the background by a polynomial in this one, and by choosing in an OTSU method, automated. And we publish it in Mehmeta 2019. You can see the details. And we're not done, because as you saw that we have the filaments, and until now we calculated the flux density, the total flux of the dust. But who said so? Who said that all the dust are described in the same way in all the region of the Crab Nebula? What if in the filaments we have more density? What if they are colder? What if they are? We are curious to know how the temperature and the density goes with the filaments. How many filaments? How we can do them? So to be able to do that, we have to be sure of what background we are going to use. So we will also we are working on a work that will be published. It is kind of innovative aspect of our work. We use a modern processing technique. It's called inpainting. I think that some of you know about it and some not. It's to better represent and after subtract the background or the foreground emission. And when we are sure about what we are observing, we can then do like high resolution, spatial, and speed and temporary resolution for the filament. So this is really, and the method of inpainting, what I will show you here, thank you, Jean, for preparing this. I don't know if he is with us for those slides. So we tried until now to do this method, to take rid of the background. So until now, like I don't know what hour it is. Until now, the background is reconstructed by linearly propagating the flux intensity. So I repeat, we choose the mask of the region of interest of our Crab Nebula remnant, we take it off, and then we try to reconstruct by linear propagation what is going on around. This creates a smooth region. It's not really representing what you are seeing. And you can see on the image on your left in the screen and on the right. On the left is the source extracted, and on the right is the background related linearly. So you see that it's not that representative. But what we're developing here, we are making now use of image inpainting technique. This technique will reconstruct the background patch by patch. So like we take like 4x4 patches, we copy them, we see the best intensity that they are present around, we copy them to have the great, if you want, a tendency to have the same profile, if you want, of the background. So the result here, on the left you have the source region of interest. We take it out, we simulate, we reconstruct the complex background by 4x4 patches where we see the highest intensity, and we put them, and you see that it is far way better. Look at this one, linear. So this linear, when I'm going to construct it with the source itself, it's going to have a problem with my values. And this is really a more realistic one. So to finish, I will finish with that. To finish, I will tell you that the work is not done yet. We're not done with calculating the dust, the mass dust, and maybe also we need to emphasize on the photometric method to estimate the flux density and not just the composition of the dust. If it is 20% carbon or silicate or other composition. And once we are sure of what we are observing and what is emitting who, we can then go into the study of the filament of this carbon. And I'm done. Thank you. Your questions.
Thanks, Cyrine, for the amazing talk. It was really very interesting. So we are welcoming any question from the participant first here.
Can I go in, please?
Yeah, go ahead, Taysir.
First of all, I'd like to thank you, Cyrine, for such an amazing conference. I've been waiting for this for a long, long time. I have a two-part question, actually. The first part is, what is the difference between the nebula and the supernova? I mean, do they have the same chemical composition or physical properties? The second part is a bit weird, I know that. Actually, I read an article a few days ago, and it says that humans and their galaxies have about 97% of the same kind of atom. And since you said that dust are formed essentially by carbon and silicon, so what do you think about the idea that a human can be originated from stardust?
Oh, can I answer the second before the one?
Yeah,
the first one?
First.
Yeah, we are stardust. Actually, we are made by star explosions. And if the stars are not here and they are not dead and they didn't sacrifice themselves, we are not here. So every single part of your cell and my cell and my body is like a star and stardust, is like the universe. We are made of carbon, of oxygen, of helium, of nitrogen, and kind of the same proportion. So we are, my dear stardust. No question. And yeah, so the first one, what is the difference between a nebula and a supernova? Well, actually, the supernova, it is the action of explosion of a big star, right? So when it is, we have this big explosion, gargantuesque, as we can say it in French. So it is supernova. A nebula, it is what is left or after a supernova or after a star is just losing its shields. A nebula, if you want to say, like a small cloud that is staying here in the space, the big space, okay? The compositions can be different, of course, because the supernova is just an evolution and it wants to explode, you know, from the iron to other. And the nebula, you can just have carbon, oxygen, helium, you know. A nebula is kind of static materia that they are traveling in space, you know. Just, I don't know if I answer your question.
Yes, that's what I needed to know. Thank you.
You're welcome. Other question?
Hello, can I ask?
Yeah,
Yes,
go ahead.
Thank you, Doctor. And are the effects of supernova explosion found in carbon in marine fossils?
I don't know if I heard very well your question. The explosion of supernova, how it is in carbon?
Yes, found in carbon in marine fossils.
Found in carbon in marine fossils. Sorry,
Yes.
I just want to make sure. So you said that some cosmic carbon was found in the carbon of the marine fossils. This is the question.
Yes. This is question.
Well,
yes.
Yes. Well, just let me tell you, I will answer your question, but I want to emphasize on something. Not all the stars will end up by supernova. Just the big stars, when they have big mass budget at they burst, they will do a big explosion, you know. So if they stop just small stars, they will just go to like a nebula, and they will end up with not a supernovae, like white dwarf or something else. But if you have supernovae, means that you are expelling, you are done with the carbon and oxygen, and you are forming more and more iron. And after the carbon and oxygen. So when you are expelling your carbon, and we have more than 3 supernovae in the local bubble around us. So the Earth passed, and the sun, the solar system, passed through minimum 3 supernovae. So it is very normal to find cosmic carbon in anything and in everything on Earth. So it's not a surprise. Let's go back to what I think I had a question if we are stardust.
Yes.
Yeah.
Thank you.
Yeah, welcome. Other question?
So I have a question from our Facebook pages. So there's a question raised, say that this dust, he means or she means the dust of the supernova.
Of course.
Can we take any information about the old universe? So if it is yes, how do you study it by using spectrum of lights?
Okay, yeah. Well, it's a very interesting question. Thank you, because and this is why I showed this picture, this image of observation in 2019 of the very old explosion in dust. Well, any light that comes from a very distant target or object can give us information about the beginning of the universe. You know, because the light has a fixed time, fixed speed, and x is equal vt. So any light that propagates from any source, to start by this, right? This is the first thing. The second thing, when you have emission from a primordial dust, the emission of a primordial dust, when I detect it, what I detect on Earth. Imagine that this is my detector, and the light will come and hit my detector. Let us take the photometer. So when the light will hit the detector, I am going to know a lot of things with this light. By its wavelength, I will know its temperature. By the temperature that arrived to me, I will know the temperature of the dust. And by the temperature of the dust, I will know what happened around this dust. And by the processes, what happened around the dust, I can know how many explosions of were there in 13.2 billion years. And by knowing the rate of explosion of supernova, I can know the rate of explosion of stars. Then I can know if the cosmos were formed with stars at one time and everything is related. So yes, with one light coming from one photon, coming from one dust, we can know a lot of things. Oh, hello, Yusuf.
Yes, another
in
question.
Jamaica.
Yeah, it's in the beach, you know, a swimming
Yeah.
pool. Oh my
So I have
gosh.
a lot of questions for that. I turn my cam. So I have another question from our Facebook page. So the next question says, so when the last supernova happened in our galaxy? So I think you mentioned it, but maybe just kind of remind.
The last one happened in our galaxy.
Yes.
I think that there is a listen. When I say that the rate, I have a lot of things to do and to say, and I just have 1 month. One, the rate of supernova is 1 per 100 years of explosion, if we can see it. Okay, this is the rate plus or minus 20 years. Second, the last one observed, I think it was what is SN 1989b. So it was in 89, but it was not observed with our bare eyes. And we were not looking at the sky and, oh, hey, look, it exploded like this, okay? It was observed with satellite, telescope. And what I want you to know is even that if we saw an explosion of a supernova, it has exploded anyway, years ago, because it is like 50 light years or 358 light years. But the light came to us now. And the third part of this answer of this question will be, everyone is talking about Betelgeuse.
Yes, that's because I have a question of that too, because someone say that if it exploded now, so how it's going to affect us?
Yes. Well, the kind of stars are very غنوجين, they tease us as scientists because they oscillate in emission. So when they oscillate in emission, sometimes they are so emitting, sometimes not, because they oscillate, they are variating, and we don't know if they will explode in 20 years by now or in 100 years, but it will explode in this century, right? And what will happen when this Betelgeuse will do a supernova explosion? Or we will have for a few weeks 2 moons in the sky, and it will be very beautiful.
2 moons?
Like the light of the supernova explosion, when it will explode, it will be like the moon, okay? We will not have a formation of a new moon, but the light will be, and I mean that we will have like sunsets, we will have 2 sunsets. It will remain here for a few days, but it will not affect us, our daily life. It's so far. Of course, we will have some cosmic rays and stuff.
Yeah, this is. I think this is what they mean by the question. So something that can affect the humans. So some rays, something like that. But if something happens in this space, it's okay. So we can enjoy it. So no problem. We have many. But the problem, it's maybe gonna. Some people saying that maybe it's gonna be end the life of humans on Earth. I don't know.
I know. I'm telling you. I know. I have the answer. No.
That's great. We're fine.
Yeah. So I have the answer for you. The meteorite that is going to hit the Earth and kill the humanity. Betelgeuse, even if it will explode, it will be just beautiful. And for the moment, if the human will not kill the human, we are fine.
Okay, that's great. So I finished my question from the web page. So if someone has any go.
Thank you, Yusuf.
Welcome.
Okay, Cyrine, we do have like a couple of questions. The first one is from Jean Garbel-Tadors. He say, can you tell us more about James Webb Space Telescope and what to expect to see with it?
With the James Webb Space Telescope, yeah, thank you so much for the question. Well, I hope that James Webb Space Telescope is postponed more and more to be launched. Well, James GWST is going to be very big. It's going to open mirror in flight. So because the mirror of James is so big, so we cannot put a 6.4 meter diameter in a fusée. How we say it in English? In rocket. How we say it, Maisa, in English? In rocket.
Yeah, rocket.
Yeah. Okay, so yeah, in a rocket. We thought about doing something like the honeycombs, and we close it like this and we open it in this space. So this is the first thing that is really very new for James Webb Space Telescope. The second one is that it's going to be very far. So the Earth is here, the Moon is there, James Webb will be here on the L2. Means that it will be zero pollution from anything that is related to the Earth and to the Moon, the light of the Moon. And what you're expecting, we increase the sensitivity, we increase the resolution, because that when you increase the diameter of the mirror, you have more light, so then you can increase the signal over noise. So your signal is up, your noise is very, very small, and we expect to see, 1, more extraterrestrial planets, 2, more region of formation of planets, because when the stars will form, at the formation will collapse, they will form kind of disk, and in that disk there is the formation of the stars, of the planets, and we are going to observe more and more in details of this, and we are going to observe very far in the universe. We are going to search and to observe the light from the beginning of the universe because of the very big mirror, because of the distance, and because maybe we are going to understand if we are an expansion or not, or kind of stuff like that.
Okay, thank you so much, Cyrine. We do have two questions about supernova. The first one, what causes supernova? And the second one, how long do the supernova last?
Okay. When you lose your equilibrium, you lose your life. Even stars understood it. You know, stars understood a lot of things that to live long, you have to stay thin, because the heavier the star are, the fastest they will die. And the second, when they lose the equilibrium between, on each level, between the radiative pressure and the gravity, because on the gravity we have a pull toward it, and the light will do radiative. When you lose the equilibrium, stars will explode. And this is why supernova exists, because there is no more matter to protect the radiation effect. So there's no equilibrium between the fall of the gravity and radiative emission of the light. And this will be the extinction.
Okay, another question is, what scientists learn from the study of the supernova?
Oh, well, supernova in general are really very interesting. We can study the cosmic rays, we can study the neutrinos, because in this equation, the small cuisine that I talked about it in the carbon-oxygen explosion, we have things that they are going out from the, so neutrinos, those small particles that they don't really interact with matter, so we really need to do things to detect them. They can tell them about the expansion, I told you, of the universe, the formation of other stars and planets, and maybe life, etc. So supernova, you know, from birth to death, the interstellar medium is a cycle. It's a very example, a good example to recycle. It's a cycle, very eco-friendly. Other questions?
Yes. Hello, Cyrine.
Asma, go ahead.
Thank you, Cyrine, for your talk. It's very, very interesting. So my question is about the plasma. Is the supernova or the nebula it's made of plasma or just dust?
Well, no. Yeah. Well, what is your understanding as plasma? Your understanding of plasma is. Can you tell me what is your understanding of plasma? Because I had the discussion and I knew that you mean the plasma, like one can imagine that is in the sun.
Matter, like solid matter, liquid matter, and
yes, and the fourth. Yes. So just for the people who are, thank you, Asma, for the question. The people who are listening to us, we have solid state, liquid state, gaseous state, and plasma. The plasma, those are some particles very excited, very hot, and we have plasma in the explosion, but they are very faint. I mean, they are not dense, but of course we have plasma. But you cannot imagine them like the density of the sun.
Yes.
You know what I mean? They are not so, because the density is so open, so distributed. Yes, of course we have plasma, and high plasma region after the supernova. Yeah. Excited plasma, crazy H2 region.
Thank you so much.
So, the gravitational collapse of supernova is really higher. So how could the external layer of the supernova escape this gravitational collapse?
So what is the temperature, how it has to be cooled to collapse? What is the value?
Not how the external layer of supernova could escape, could like go far away from the gravitational collapse.
Yes. Because of the loss of the when it loses the equilibrium. Actually, what will happen is when we lose the equilibrium, some particles will go out, the lighter one will go out, and we still have the carbon and oxygen, what is left in. Because a star, you have to keep in your mind that a star is a nuclear chain. So it's a PP chain or CNO chain cycle. What is a PP chain? Let us take a PP chain. Proton-proton chain. The proton-proton chain. They fuse and they will form helium with neutrino and stuff. So the number of particles, the number of particles is increasing. We have the gravity is not sufficient enough, and particles lighter are leaving. Helium, hydrogen, they leave, and what we'll have after the nuclear reactions, we will have carbon and oxygen. At that state, something will happen, it will start to oscillate, and if there is mass enough, they will collapse under the gravity. They will form do a chain of CNO chain of nuclear to form a bigger element than CNO, and after a certain time, they are so dense that we can go denser, you know? It will be at the repulsion of the electrons. The electrons, if you push them like this, you cannot put them negative will, and then they will explode. This point, if it is a big star, what will do the explosion of supernova.
So if we consider our sun, how much need our sun to be supernova in the future?
Oh, our sun is not a supernova. No, our sun will end up just to be a nebula and a small white dwarf within it, because to be able to do a supernova, you have to have stars bigger than 8 solar masses, 10 solar masses. So our sun, when the layers will go away, the surfacic layers, it will end up to have carbon, oxygen, and then a white dwarf nebula and white dwarf, small white dwarf, because there is no supplement, there's no mass budget in the star to form a supernova. It's a small star, our sun.
So can a supernova give like black hole in the future?
Oh, everything depends on
the mass.
So if a star is huge, the initial mass, yeah. If a star is huge, after the explosion inside, if it is equal or bigger than the 3 solar masses, the wedges, what is left, it will be very dense, a lot of material, and we form. And if it's not, it can be a neutron star or a pulsar, like we saw on the Crab Nebula, if it's not that big.
Okay, from my part, I finished it. I don't know if you do have some question, guys.
So I have another question this time for my side. So for supernovas, for example, in other galaxies, can give us any information about the star formation rate in this galaxy?
Yes, always when we observe, we have model simulation. So if we observe now a new one, we can add it to the data. We can have a lot of wavelengths with other, the high energy also will give us another window to other what is happening inside of it, and it will give us information to what's going on in our local bubble also, of course. Everything, it's not just guessing, it's not a guess. So what is fantastic with a theoretical model or a simulation is that you have your observation, you do your simulation and your theory, and then you compare it with your observation. If it explains somehow, you're happy. You cannot change your observation. They give you light. gives you light. But what you can change is the physics that you're using. So you change the model, you adapt. Yeah, you know. So maybe we are going to adapt our understanding for the explosion rate or explosion energy. It would be fantastic. Yeah.
So I think you didn't explain about the type of supernovas. So
everything explain. No. The light can explain of the type of supernova because.
Just my question is for you. So I think you did mention that in your presentation. If you can give us some details so that they are listening to us, which kind of supernova that we have in general, and how we can, for example, identify this one is type 1 or this one is type 2 or something like that.
Yeah, well, there's a difference. I didn't want to go into that. So if they are binary stars, you see, I didn't want to go in that, Yusuf. So there are two kinds of supernova. Mahek, Yusuf?
Yes,
so one one that they can be kind of binary stars means that they are in twins, rotating, two stars rotating together, and when they are done with all that matter and materia, they stay with a white dwarf. Yani they are get rid with hydrogen, helium, whatever. They are just rotating as a white dwarf. But here we have a young star. This young star will start to feed the other one. And the white dwarf is not a stable thing. You know, if you put it, it will not be stable. So then it will explode. And the other kind of supernova is the big one that will end up kick H, kick helium, lithium, beryllium, boron, carbon, and we are iron to the explosion.
So we can't identify
yes.
the emission lines that we have on our speaker, right?
Yes, we can identify them by which experiment or not. This is the first one, and the second one we can identify them by the intensity of and by the time of the explosion, because one is so intense, very short, and the other is less intense but stays 3 to 4 weeks.
Okay. Yeah, the time of.
So we have two kinds.
The time of explosion. So then you can say that from the light curve, from photogrammetry data, or basically your photogrammetry data.
Yeah.
And I will mention that also some astronomer amateur helped on that too. So because sometimes we don't have a lot of time on big telescopes to take a lot of data. Astronomer amateurs look in this when we have explosion, and they have really high magnitude, and you can observe and give us many points, and then we can make our life. Okay, thanks.
Yeah, and I photographer. I wish, but I don't have one. We have good astrophotographer in Lebanon.
Yes, also too. By the way.
Yeah, you know.
So, by the way, in Tunisia too, huh?
So, okay, sorry. Yes, Yusuf, you were saying. Sorry,
I say that in today's we will have a talk about astrophotography. So we have already one in Arabic, and so we are organizing many talks, and we will have also another one.
Great, I will be there.
Tomorrow. Okay. And the idea is that astrophotography is nice, but you know it sometimes needs some material and some. But this organizing this talk to tell the people so we want to do astrophotography and to be an astrophotographer. Something like that.
Yeah, so if you know, I can speak for 2 hours.
Yeah, sorry.
Because I read. So, Maisa, shall we?
Yeah, if we don't have any question for Cyrine, so we can like close here. No more question. Okay, so thanks Cyrine for the nice talk today. Thank you, Cyrine, so much for your time and for the presentation. It was really amazing. So have a nice time and see you the next time. Thank you. Bye bye.